بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين. Well, this is going to be a very quick, or I try to make it quick, video about decision trees. Why I consider this worthy of having a video on it is simply because there are some, I don't know, misconceptions about it, and also because it's related to one of the advanced machine learning algorithm, which is XGBoost, and it's worth having a solid understanding of it before going any further. So a decision tree is a supervised machine learning algorithm that is used here. It's mentioned for classification, but also I think if you revised your lectures in decision trees that are or were used in XGBoost, they are also used for regression. So decision trees is not only limited to classification but also can be used for predictions in regression. Well, I'm not going to dive very deep in every detail here, but what I consider very important, especially for the practical side and the computational side. Well, these are some concepts concerning the decision trees and its architecture. And here is the most important part. Why it's important? Well, we say a decision tree, so it's a division. A tree is made of a trunk, then the branches, then the branches get divided into branches, and so on till we have leaves. It's the same. This is the main trunk, then it will have branches, and the branches get into new branches until we have leaves. But how we decide what this is the trunk, the main data, and when we go into divide it, we've got to divide it according to one of these features. Are we going to divide it according to age or income, students, whether it is a student or no, credit rating, and so on? And why this attribute selection measure is very important. In this example, we only have 4 or even 5 attributes or features, but in real cases we will have so many more, and we can't just decide without any solid foundation. So we've got to pick the best to start with and stop when we are required to stop. So we are required to pick the best features that yields the best divisions of the data set. And it's called attribute measure or attribute selection measure. The attribute is the feature, so we are selecting the attribute or the feature that we are going to use in our splitting. It's the splitting criterion. And how it works, we will see them, but in one single word, it gives us a measure how it is affecting the split. Is it which one of the features is the best for splitting? We have 3 ASMs: information gain, Gini index. By the way, Gini is an Italian scientist called, I don't know what, Gini, and gain ratio. You see here it's information gain and this is gain ratio. These two are related and this one is more specific. Well, as I said, I'm not going to get into all the details, but some key information. So here all it's based on the entropy. Gini, not the Gini, information gain and gain ratio are based on the entropy. What is the entropy? It's voila, it's here, but we can speak about it graphically. When we've got a data set, if for example we have success and failure, we have 50-50, so it's the highest level of uncertainty. So when 50-50, the probability is 0.5, so the entropy is at its peak. But if we have either 1 or 100% or 0%, it means it's pure or clean. This is very messy, this is pure. So entropy here equals to 1, and in both places equals to 0. These are the formula for that. Information gain. So what is information gain? It's simply the measure of change in entropy. We know entropy is the measure of uncertainty or messiness, how dirty is our data. So the more we reduce this dirtiness or messiness, the better. So we gain information about that. This is why it's called a gain. The more we've got, the more the difference is, the better we are. So for example, if we have here a 1 and after splitting we get 0 or close to 0, so the information gain will be big. So it's a positive, it's a good. If it's not, it's bad. And then we compare between the attributes we are using. So here this is calculated for each attribute. When we go to our dataset, we suppose we are going to do that for age. Age we have youth, middle, and senior. So we're going to do it. This is the I. So we're going to do entropy after split for. It's all for age, but firstly for young, then middle, then senior. This is where we use the I. So we can write this formula by saying entropy, this is the root, and this is the entropy of a specific attribute, say age or income or whatsoever. So in this example we are going to try to compute that, well, the information gain. This is just extra explanation of what we are doing here. So in that example we've given a data set that we will apply information gain as an attribute selection measure. So we are going to test all our attributes and see which information gain is the best. So we start by, before the split, we calculate the entropy of the dataset before the split, and it equals, you already have the formula for calculating the entropy. It's well, it's up here. So for this we can call it the before, or more technically speaking it's the root data set. So you see the entropy is 0.94, and this is very logical since we've got nine yeses and 5 no, so the degree of uncertainty is kinda high to quickly tell or predict what will be the output. So as we said, we start by the entropy of the root or the before or the dataset before splitting. Then we move to all the attributes. We measure the information gain for each attribute. For example, age, we have 3 cases. We measure each one of them. Entropy of age equals to 5. Why it's 5? We can go to the Excel file and I will show you why. We have we have 5 and 0. We have 5, 4 and 5. Let's remove this. When we pick the age, middle-aged, we have 4. As you can see, it's 4. All of them are yes. It's 4 over 4. 0 are no. This is why we put our 0. We go to senior. We have 5, 2 are no's and 3 are yes. Senior, 3 yes, 2 no's, total is 5. And finally, the youth, 3 no's, 2 yes. Youth, 3 no's, 2 yes, the total is 5. And you measure all the entropies. You apply the calculation here and we end up with the entropy of age. To compute the information gain, it's very straightforward. We get to a 0.246. The same way we measure for the information gain for income, students, and credit ratings. The best is the highest. As we said, it's an information gain. There is a gain. So, as it says here in the conclusion, age yields the highest information gain compared to the others, so it is selected as the root node. So we will split our trunk or our original data based on age, as you can see here. And we will do the same process. We will not do it here because it's clear, it's a pure data set. We will do the same for this one. We will have an entropy for this data set. We choose the attribute, we do the same here, and we choose the attribute. The same process will be applied to each partition until all tuples of each partition belongs to the same buyer computer class in order to distinguish. Well, we will do it until we got at the end clean subsets, or we run out of criterions, or at some stopping levels, stopping criterions. Well, that was the information gain. It's very straightforward, as you can see. Now we go to the Gini index. As I said, it's a scientist name. The Gini index evaluates splits by measuring the dataset impurity. Here, this is a key element. It measures the dataset or evaluates splits by measuring the dataset impurity. So it tests the yielded dataset by impurity. So intuitively, we are supposed to find low impurity. The lowest, the best. It is a cost function that favors larger, cleaner partitions. The child decision tree based on Gini index, we should follow the COT classification algorithm. Well, this is the formula for Gini index. As you can see here, higher Gini indexes mean higher in quality or impurity. The the purity of the node describes how close the node to the containing data from only one class. So the lower the Gini index, this is the criterion, the lower the Gini index, the lower the probability of misclassification. And it's logical. Lower Gini index, it means the data set is getting cleaner, so the misclassification is getting higher. So we are going to do the same as we did with our first example of information gain, but this time we're going to measure the Gini index for the root data set and for each of the attributes or the features. As you have seen now, you know what is this 3 and what is this 2. You apply them directly. We compute the Gini index of each of them, and at the end we got this. You remember, for information gain, the higher the better, but for Gini index, which one is the lowest? It's clear, it's the mod.343. This is a 3736, so we pick the Gini of age. Now, as you remember here, because the process will continue and it will not stop here, after we finish this one is better. Like we did with the root dataset, now we have two unclean datasets. We will measure the Gini index of this and get the splits. Then we do the Gini index here and get the splits too. And as you can see, for the leftmost we have the center, the left and the right. The right, if we have the middle age, it's a direct prediction that it is a yes. If our age is middle aged, so the prediction is directly yes. But if it is youth or senior, we can't say. So we went and tested on student. We did the Gini index for that data set, and we decided that student feature or student attribute is the best to do the splitting. We completed that, and the last, well, or the remaining feature or attribute is applied here, and we got a complete decision tree. The gain ratio, finally, the gain ratio, as I said earlier, it's related to information gain. They share the same word here, which is gain. What is very important about this, look, if we go back to our data set, if we go to our data set and accidentally we use this as feature as an attribute for selection, we will end up with pure data set. We have one element with 100% no, one element 100% no, one element 100% yes. So the first data set 0, second 0, third 1, fourth 1. So the purity or the entropy equals to 0. Based on information gain, we would say that this is a perfect. You might say that it's an ID, but suppose you have a misleading, like the birth date, or you don't know about your data set, you're not an expert in that field, and that feature's kinda useless and it's misleading. If you use information gain alone, it will give you very high information gain, but it is meaningless and it will lead to overfitting. Yet based on the mathematics, it's very good. So they suggested the gain ratio. Well, it suggests I'm trying to explain the intuition behind it. The gain ratio, it takes the info gain but divided by the split info. It kinda of penalizes. Look, if we created so many data splitting but they are meaningless, it will penalize it. You can apply some examples of, for example, if you have a data set or a feature of a data set that will split your data into 4 equal subsets, so it's going to be 0.4, 0.25, 0.25. When you measure this log, you will discover that the information gain getting reduced. But in one single word, as it says here, the attribute with the highest gain ratio is chosen. Always we are concerned with the highest. Why it is chosen? Because the split info didn't affect it, or the split info is going to be very low, so we keep the information gain advantage or increase it. But if the split info, we are creating useless data sets, it's going to be higher, so it's going to reduce the ratio of the gain. That's it. It's just to have the intuition about it and don't dive any deeper.